Welcome to my video course on engineering FRMCS. Today, we're taking on a massive, honestly vital topic, demystifying the overarching architecture of the Future Railway Mobile Communications System, or FRMCS. We're going to break down exactly how modern railways are going to manage the just unimaginable flows of data needed to keep trains running safely, efficiently, and automatically. And to really get our heads around that, we have to look at the very foundation of its design, the three stratum layers. Here's our roadmap for this explainer. We'll start with an architecture overview. Then we'll explore the railway application stratum, the service stratum, the transport stratum, and finally, we'll wrap the whole thing up with the multi-stratum security model. Let's jump right into Section 1, the FRMCS architecture overview. You know, legacy systems like GSMR, they were built as these tightly bound monoliths. Everything was locked together. But modern rail, it absolutely needs a new paradigm. Enter the stratum. By definition, a stratum is an abstraction layer designed to enable complete independence between the railway applications and the underlying physical transmission technology. Think about it. Trains are on the tracks for literally decades, right? But telecom tech? That evolves every few years, so separating them is absolutely crucial. It's what ensures future-proof interoperability. This architecture separates responsibilities perfectly. As you can see at the very top, we have the Application Stratum. This is where your train controls and user interfaces actually live. Right beneath that is the Service Stratum, basically acting as this intelligent middleman. And then down at the bottom, the Transport Stratum handles the physical radio waves. The beauty of this is that they communicate through standard interfaces, but they remain completely functionally independent. Moving on to Section 2, the Railway Application Stratum. Future rail use cases are, well, they're intensely demanding. We're talking about ETCS Level 3 moving block, automatic train operation, remote driving, and even live onboard video surveillance. These applications generate just massive signaling and data requirements. Take moving block technology, for example. It is entirely train-centric. It requires these continuous, ultra-reliable streams of location and train integrity data just to allow trains to safely travel at minimum distances from one another. Honestly, the sheer volume of data we're dealing with here is exactly what's driving the need for this new layered architecture. So, the really crucial question is, how do these high-level applications actually talk to the layers below them? Well, we have two main regimes to look at. First up is tight coupling. This is where the application directly utilizes mission-critical, or MCX, service primitives, so it's actually aware of the telecom network. But then, on the flip side, we have loose coupling. Here, the application remains strictly independent of the telecommunications technology. Now, why does this matter so much? Because your vital systems, like automatic train protection, they absolutely require loose coupling. They have to stay totally isolated from any telecom shifts. Think about it. If the network upgrades from 5G to 6G overnight, that vital train application shouldn't even notice the difference. It just keeps working. Okay, let's dive into Section 3, the service stratum. So what's actually inside this middleman layer? Well, to quote the official requirements directly, the FRCMS service domain shall include an MCX infrastructure, including a SIP core. Essentially, what this means is that it relies heavily on mission-critical service frameworks and session management protocols. The SIP core, for instance, is just a highly standardized way of managing multimedia sessions. It was actually originally pioneered for public safety networks, but now it's being adapted for the split-second, life-or-death demands of high-speed railways. Within this service stratum, we're really talking about three key things: identity, roles, and session management. This stratum entirely abstracts all those messy network complexities away from the applications sitting up top. It's down in the weeds, managing user tokens, dynamic group communications, and location-dependent addressing. And it does all of this without the train application ever needing to know the how. The train simply requests a secure communication line, and boom, the service stratum does its thing to establish that session. It's seamless. Next up is Section 4, the transport stratum. Let's actually trace the flow of data across the 5G hierarchy here. Step 1, it all starts at the user equipment. We're talking about the actual radio modules sitting right up on the train's roof. Step 2, that signal beams out and hits the radio access network, specifically those trackside 5G cell towers, which are known as GNODB. And finally, Step 3, it travels deeper into the 5G core network, all the way down to the user plane function, which actually processes the payload. And there you have it. That is the literal physical journey of your data. But here is a truly defining, strictly enforced feature of the Transport Stratum. It is radio access technology, or RAT, agnostic. Now, yes, FRMCS utilizes 5G today, for sure, but this transport layer is intentionally designed from the ground up to support multiple radio access technologies. It is built to survive future evolutions. The entire ecosystem is structured so that the underlying radio tech can literally be swapped out without collapsing any of the higher strata. Talk about future-proofing, right? And this brings us to what is honestly an incredibly surprising and powerful feature: multi-path capabilities. See, the Transport Stratum doesn't just rely on one single connection. No way. It can utilize multiple radios simultaneously. It connects to different transport domains at the exact same time. So if one radio signal suddenly drops because the train zips into a tunnel, it's no problem. The other radio is already carrying the payload. This kind of vast redundancy is what increases connection reliability to those ultra-high, fail-proof standards that fully automated trains absolutely require. Now for our final piece of the puzzle, Section 5, the multi-stratum security model. You have to understand that security here isn't just some perimeter wall you can hop over. It's a strict defense-in-depth approach. Security is applied independently and uniquely at every single stratum. So if an attacker somehow manages to breach the transport layer, they just hit a completely independent security wall waiting for them at the service layer, and then yet another one at the application layer. It's literally built into the stack's DNA. Let's quickly break down those core security functions. Both the service and the transport strata independently perform access protection. That means strict authentication to ensure that only authorized modules actually get on the network. They also both independently provide integrity protection to guarantee the data hasn't been tampered with in transit. And of course, they both provide confidentiality and privacy protection through some seriously robust encryption. It is essentially a stacked vault, ensuring malicious actors can't interfere with vital train data at any point in the communication chain. Which really leaves us with a final thought to ponder here. If the transport stratum is strictly RAT agnostic, and the vital applications sitting at the very top are completely decoupled, just how seamlessly will this entire layer cake adapt when 6G inevitably arrives? The entire architecture is designed with the explicit promise that these massive trains won't have to skip a single beat. Thanks, we can see you next video.